So last term, we finished off looking at quadratic functions, and this is going to be a kind of pattern that we repeat a number of times for a fair whack of the year. We're going to look at different function types. So we're partway through a unit called polynomial functions. And polynomial functions, if you remember, has a leading term, so something x to the power of some whole number, positive whole number, and then plus x to the power of something else, plus x to the power of something else, all whole number positive powers sort of thing. We're going to look at other functions as well, including trigonometric functions, exponential functions, logarithmic functions. And the idea really, I mean, the big picture stuff is that if you're a scientist or a researcher, what you do is you capture data for some sort of situation, and then you plot that data, and then you look at the data and say, oh, this looks like it might fit a cubic function, or a power of 4 function, or it might be exponential, or it might be logarithmic, or it might be a sinusoidal, whatever. The data tends to follow a certain pattern, if it does have a pattern. And then what you're trying to do is trying to work out a function that fits it. Because once you've got a function, then you can do things like look at initial values. You can predict somewhat into the future, not too far, because it gets a bit unpredictable the further out you go. It's called extrapolation. So, but you've got some sense, and you can look at data points that you don't actually physically have a specific collected data point, but it exists between two other data points, and you can extrapolate what that should be because it fits this kind of pattern. So that's the big picture stuff. That's why we look at it in methods, other than just because you've got to be examined on it. But ultimately, what you want to do in a function study then is pretty much the same thing. You want to get a sense of what the shape of the graph looks like, so that when you see something, you go, oh, that's a cubic, oh, that's a whatever. Secondly, you want to be able to identify critical values. So the critical values tend to be y-intercept, zeros, x-intercepts, if they exist, maxima, minima, there may be more than one. In a quadratic function like this one, there's just one. This one is a minimum, it's a turning point. Other features as well. So, for example, in an exponential graph, there's an asymptote. In a logarithmic graph, there's an asymptote too, but it's vertical. In a trigonometry, well, in a sine or cosine graph, there's an amplitude and there's a period and all that kind of stuff. So each graph type has its own special features that you need to try and identify. Good so far? Okay, so what you see in front of you, this is just not even revisionary, it's just a build-up for looking at cubics, which is the focus of the next bit of the term. In fact, cubics is the biggest polynomial we look at. So this quadratic graph here, just to remind you then, as x goes further along this way, we see a more or less exponential growth. It's not linear, it doesn't go straight up like this, but if I go across 3 units, I'm going up quite a huge distance to get to the graph. If I go up 1 unit, I'm just going up a little distance. 2 units, quite a big distance, and so on. It's a squared relationship, which is actually an exponential one. It's not an exponential graph, but exponential in terms of it grows quickly. And we can see here that as x gets bigger but negative, it is also growing backwards. Or to put it a different way, as x approaches 0 from the negative side, it's exponentially getting smaller. So the jump between here to a -1 is all the way along there. Between -1 and 0, it's just a little distance. So it's growing smaller and smaller and smaller and hitting 0. But it's positive, of course, because any number squared is going to be a positive value. So although the domain, remember, Dijkstra, have I gone through Dijkstra with you? I don't think I've done domain and range with you, actually. I'll have to do that. But the domain is all possible x values. D for domain, I for input, x for x values. So Dix, and then the output is range. That's all the possible y values. Output y. So Dijkstra. So the domain, all possible x values, is every single possible one. I've just got the whole numbers here on this graph, but it also is every single value between 0 and 1, an infinite number of values between here and here, and so on. So it's all possible values for x, but the range, the possible output values, the y values, is just everything, including everything positive as well as 0. We never hit a -1. Now, what do you think y equals x to the power of 4 is going to look like? And then what? Go for it. Wobbly like that? Okay, let's see if you're right or not. 3 turning points? Not 3 turning points in this instance. Not 3 turning points in this instance. How could we have explored this? We could have explored it by putting in a few values to see what happens. But perhaps if we look at it logically, Sam, thanks for actually having a crack at it, though. I really appreciate that. Is maybe if you think about it, it kind of makes sense in that it's basically the same as the x squared graph, except that after 1, in other words, when it's sort of, it's bigger than 1, it's accelerating faster, which kind of makes sense because we're raising the value to the power of 4 instead of to the power of 2. So every value is increasing even higher. So 1 to the power of 4 is the same as 1 to the power of 2, which is why it's the same there and there. But then for 2 squared is 4, but 2 to the power of 4 is 16. So we'd have to zoom out a fair bit just to get to the same value, 2, and there's 16 there. Okay, so it's accelerating faster. So, maybe when you think about it, unsurprisingly, it is the same sort of parabolic shape as x squared, but just a lot faster. But then when you look at close to 1, can you see how it's flattened out? It's actually moving slower than an x squared graph. Okay, so it's moving slower because when you take a fraction and raise it to the power of 4, it's going to be an even smaller fraction. You know, like half squared is a quarter, but a half to the power of 4 is a 16th. So between 0 and 1 and 0 and -1, it's slowing down because the fraction's just getting smaller. The output fraction is getting smaller. Then after 1, when you square or power of 4 of a number, it's getting much bigger. Does that kind of make sense just from a verbal description of what we're doing here? So let's have a look at this one here. What would you expect to happen for, I might just do it actually, but maybe you might have a sense of where the x cubed graph might be. But because some of you have done math methods, I'm not going to get you to describe it because you're probably just going to do from memory rather than what I've got here. So when I tick here, you can see this red line, unsurprisingly, fits between the blue and the green one. In other words, it's accelerating faster than the x squared, but not accelerating as fast as the x to the power of 4. That's common sense, isn't it? It's not going to accelerate at the same pace, but it is effectively a parabolic shape as well. If I just get rid of the x to the power of, in fact, if I get rid of both of those, you can sort of see it. It's like a parabola with a more flattened base, I suppose. Okay, so that's y equals, no, it's not. It's not y equals x to the power of 3. What is it? What are those bars mean? Who can remember what the bars, vertical bars on either side of a value mean? So I don't have a whiteboard marker here because it's the first day and I never remember to bring stuff. So like, for example, the bar -3 closed bar has an output of, does anyone remember what the result of that is? Oh, okay. So the absolute value symbols is what they're called. And when you take the absolute value of a number, the result is always positive. So the absolute value of 3 is 3, but the absolute value of -3 is also 3. So absolute value just rips off the negative sign effectively. Does that sound familiar? I'm pretty sure you would have come across it, but if not, I'm hoping that my description's enough to get you going with that one. Why do I need it to get this graph? Because this isn't y equals x cubed. This is y equals the absolute value of x cubed. Why do I need it? If I have it for y equals x squared, I could put the absolute value symbol around this as well, and it would be no problem at all. You'll see how much it changes it. Not at all. Doesn't change it at all. And if you remember what I said a second ago about the range, i.e. the output values of y, that would make sense why it makes no difference. I do need it here if I want to have the parabola or the flattened parabola for y equals absolute value of x cubed. Why is that? There's no trap here. It's just thinking about the values of x cubed. Even if you're used to sleeping in on the holidays, surely by 10:45 you should be awake anyway, shouldn't you? What would happen if I got rid of the absolute value symbol? In other words, I just had y equals x cubed. Describe what would happen to those output values. Okay, let's when you're confronted with a question that you can't really picture, drill down to detail by example. Okay, so narrow it down to specifics. So if I put in y equals 2, I'd get 2 squared is 4. Remember how I did that before? 2 squared equals 4. If I put in y equals -2, I get -2 squared, which is also 4, so that's fine. Let's do the same thing, but with x cubed. If I put x equals 2, then 2 cubed is? Come on, man. 2 cubed, at least you can give me that. Thank you, 8. Okay, so, and you can see that here. Oh, it's just off the screen a little bit. But you've got 2 cubed equals 8. 2. So it's accelerating at a much higher rate, but nevertheless, 2, 8, we're good to see it. Okay. If I cube -2, what do I get? Thank you, -8. Okay? So when you raise a negative number to an even power, the result is positive. But when you raise a negative number to an odd power, then the result is negative. So it's going to change the shape of the graph as a result. We no longer will have a parabola unless we cheat by putting absolute value. But that's not the graph of y equals x cubed. That's the graph of y equals the absolute value of x cubed. That's not what we want. But I wanted to show you then that if I just go y equals x cubed, and I know this is a, oh, that was good, wasn't it? It gave me the same colour. I know that this is something that you have seen if you've done maths methods before, and you don't have to have, but I wanted to present it in this way so that you can sort of get a sense of it. Okay, I'll just use my mouse cursor here just so it's captured on video. So you can, I'm hoping what you can see is that all of these negative values here in red have been reflected, mirrored over the x-axis, so they're down here instead. Okay, so this part of the graph is the same, but then from 0, so in other words, all negative values, it's gone backwards. Okay, not backwards, reflected. Okay, they're all negative values of y instead. So for a cubic, the output values are all values as well. Okay, whereas for an x squared and a quadratic, it was just positive values and 0. Okay, so that makes the classic cubic shape. I'll turn off the absolute value, and it looks like this. But I want you to see that the way a cubic works is basically one parabola here, and then a reflected parabola half here. It does the same thing where it grows from the left to the right. It starts off big, and as it gets down towards -1, it's getting smaller and smaller. And then between -1 and 0, it's very steeply slowing down, and then between 0 and 1 it starts firing up again, and then from 1 onwards it's escalating in its growth again. So you've got this basic function. So you've got a parabola. I won't see this on the video, but you've got a parabola that is swung down like that. Okay, so do you remember that for a parabola we would call this concave up officially, smiley graph, but concave up is how we describe it. And if I put a negative there in front of it, we call this concave down. So there are basically two kinds of concavity, concave up and concave down. And the axis of symmetry is at the middle there, at the turning point. So when it comes to a cubic graph like this, sorry? Okay, cool. That's helpful. what we have here is half a concave down graph and then half a concave up graph. And then remember, it's slower here, so it's not as pointy as a parabola, but nevertheless, it's the same idea. It's slowing down and stops and then starts up again. So half of it's concave down and half of it's concave up. And that means we don't exactly have, we don't have a maximum and a minimum. What we have is a point at which the concavity changes. At 0 for this basic graph or base graph of x cubed, it's concave down until x equals 0, y equals 0, and then it's concave up. Okay? Now, the formal word that we use to describe the point at which the concavity changes is called the inflection point. And I bet if you did methods, Maths Extended last year, or math methods, you'd be aware of that word, inflection. So the point of inflection is the point where it stops being concave one direction and starts being concave the other direction. Okay? If I make y equals negative x cubed, it's there, but now it's concave up until 0, 0, and then it's concave down. The point at which it stops being concave up and concave down and turns to concave down is the point of inflection. For want of a better term, it's still a turning point. It's still, in this case, what we're describing is a turning from concave up to concave down or vice versa, but it's still a turning point. Another fancy phrase you might hear is it's called a stationary point. In terms of if this was a speed graph, you'd kind of have it's really fast, it's getting slower, 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 it stops and then starts speeding up again. So this here is a resting point. So resting, stationary, not paper stationary, but stationary as in to be still. So it's a stationary point. Okay, point of inflection, you can kind of call it a turning point, although it's pretty bit loose, or a stationary point. Okay, that's the basics of a cubic graph. Does anyone have any questions? Okay. With quadratic graphs, there is really only one shape. It might be reflected, in other words, smiley or frowny, but with cubic graphs, there's really only one kind of graph, and that is it's a parabola. With a quadratic, with a cubic, there are two kinds of graphs, which I can't remember, was it you, Sam, that sort of mentioned that about, no, I can't remember who it was, you can't, about more than one turning point. You can have this part here being stretched out so it can look like a roller coaster ride instead. So we're going to tackle that tomorrow, and we're just going to focus on the basic graph here. Now, I don't know if you can remember or not, but from the quadratic work we did, we saw that every quadratic function was a transformation of the basic graph of y equals x squared. You can't say the same thing about a cubic, but you can say there are a bunch of very similar graphs to the base cubic graph as well by applying transformations also. Okay, so just to remind you, the transformations are dilations, stretch this way or stretch that way, reflections, flip this way or flip this way, and translations, this way or this way. Okay, so three kinds of transformations. And in today's lesson, we're going to focus on transformations of the basic cubic graph. Okay. Just while I'm here, reflections are probably the one thing I just wanted to quickly have a look at before I sort of make it a bit more complex. If I go to negative x cubed, it reflects over the y-axis. Yeah. So it's there, and then when I put the negative in front of it, it flips over the other way. So it starts positive and ends up negative. Now, in a quadratic, that was the only reflection you had to deal with. This is basically reflecting the output. So we've got x cubed, the basic graph, and then I've changed the output to be the opposite sign. Okay, so where it used to be negative 2 cubed equals negative 8, now negative 8 is positive 8. So negative 2 is positive 8. But something slightly weirder happens when I put the negative inside. Oh, you can't tell on this one. That's annoying. If I put the negative inside the bracket, it's actually flipping this way instead. Okay, so I'll show you what that looks like in a sec, because it wasn't that exciting here because I've got it right in the middle. So let me flick over to this function here, and again I've got y equals x squared here, like so, but now I'm going to activate this one here, and hopefully it looks similar to something that you've seen before, which is turning point form for a quadratic, but instead of to the power of 2, I've got to the power of 3. Okay, so there it is there, our classic cubic shape, where we've got concave down until we get to the inflection point, and then we've got concave up here. You can see that at 1, 1, it agrees with each other, because at 1 squared we've got 1, and at 1 cubed we've got 1. So there's a common point of intersection there. But this is basically, for this graph here, I've got a equals 1, h equals 0, and k equals 0. So I've got 1x cubed plus 0. So this is just x cubed, our base graph. By adjusting these, we can start seeing what will happen. Let's try and anticipate though. Let's start off with h. What happens, do you think, to the graph when I slide h over to the right here? Goes up. We'll have a raising of the graph. Anyone else? Or side to side, one of the two? Who reckons up? Who reckons it's going to be a, let's use the fancy words. Who reckons it's going to be a horizontal translation? Who reckons it's going to be a vertical translation? Either way though, let's just start off with the basics first. Horizontal translation or vertical translation, okay? Who reckons it's going to be a dilation or a dilation? Who reckons it's going to be a reflection? No, won't be a reflection. Okay, let's have a look. It is a translation. So in other words, it's going to go this way or that way. And as I move h positive, it's actually moving to the right. Okay? It's moving to the right because of the x minus h. If you think about it, the h is associated with the x value here, and x is along this way. Okay, yeah, it's just one of those things we just need to remember. But try and make sense of it so that it's not just a recall exercise, but a common sense click as well. That this is actually going, the minus h is going to affect how the input values are changed. And so it's going to shift the graph left and right. So when h is equal to 1, that's h, that would be a outside of x minus 1, remember, x minus 1. And have a look at the point of inflection here. It is now 0, 1, okay? Sorry, I said that around the right way. It is now 1, 0. So the h represents the x coordinate of the point of inflection. If I go backwards, h is now equal to minus 1. Let's remember how to read that. That means x minus negative 1, which you'd never write, right? What would you write? X plus 1. Minus a negative is a plus. So this would be x plus 1. So when we've got an x plus 1, it's shifting over to the left. Now I reckon we should be all right with, guess what k does? It takes the graph and it's going to add a value to it. So that it's already been calculated as a graph, but now it's going to be shifted up or down. Okay, so it's going to go up or down. There we go. So the value is changing like so. So as a result, I can shift to 1 and, oops, that's not so useful. I'll just zoom out a bit, I think. If I go 1 and 2, the point of inflection, as you can see, i.e. the place where it stops being concave down and starts being concave up in this instance, is now 1, 2. Okay, it's the h value and the k value. Is that okay? So straight away, if I said to you graph f of x equals x minus 2 all cubed plus 3, you should be able to do that because you know the shape, concave down, then concave up, point of inflection at 2, 3. Is that okay so far? Okay, so that's those ones. We've also got A. A is the dilation factor. As A gets bigger than 1, it makes the graph shrink like this. Okay, it squishes it. Let's see if you can sort of see that. It's because we're making the graph steeper, basically. So if I go A equals 2, it's now stretched it. It's now, the graph centered around here is now made thinner, I guess. So it's a vertical shrink. Okay. If I go A equals -2, then we have not only a dilation, but we also have a reflection about the x-axis as well. So there's negative x minus h all cubed, and then there's -2 like so. So it's dilated by a factor of -2, which means it's shrunk, plus it's also reflected because it's gone from concave down to concave up, now to concave up, then concave down. Okay? This is just a potted summary. Is that okay? Because you've seen transformations before, and we're going to spend some more time really formalising it a little bit later on, I'm just hoping that's good enough for you to get a sense of what's going on. The other thing that I wanted to point out, I'll just bring A back to 1 just so it's not too confusing, is that when I put a negative in front of the x in here, in other words, instead of making the whole function negative, I'm just making the x value negative. Have a look at what happens to the graph. It's gone from there over to here. So it's reflected, instead of being reflected about the x-axis, it's now reflected about the y-axis. Now, when you do that with a quadratic power of 2 graph, then because it's symmetrical, when you reflect it that way, it makes no difference. You know, the mirror image is exactly the same that way. But because a cubic is not symmetrical, then you can really tell the difference when you put a negative in front of the x. So that's a new reflection for you. This is a reflection of the input, right? I'm taking the x value and then changing it to a negative before it gets cubed. So it's reflected that way. Whereas if I do this, the x value remains the same, and then minus h, and then it's cubed, and then it's made negative. And so it just gets reflected that way instead. It's flipped that way. Okay, so it's a reflection about the x-axis. Okay, so there's reflections, there's dilations, reflections, and translations, the 3 things that will help you take a basic cubic graph and work out where it goes. In terms of critical points, the critical points are the inflection points, fairly easy to work out, but you'll also need to work out the y-intercept, and in this instance, for this kind of cubic graph, the x-intercept as well. And the x-intercept, it's exactly the same process as you've done for quadratics. To work out the y-intercept, you set x equal to 0 and solve. To work out the x-intercept, or the 0, set y equal to 0 and solve. Clearly, the solution is going to be more straightforward, more complex because of the cube. Unlike a quadratic, it will always have an x-intercept, okay? There's no above the x-axis or everything totally below the x-axis. You'll always have one, and that's because you can cube root a negative number. Like the cube root of -8 is -2, for example. Anyway, I'm over talking. I apologise for that. So on Google Class, I'm not going to go through any worked examples just to see how you go. But on Google Classroom, in that functions schedule of work, I've updated it just for this week, and you can see, and I can leave this on the screen if you like. You're going to be going through exercise 6E, and again, I've cut down to just the fundamentals there. If you go through these and you've still got time left over, you can of course do more. Or if you feel like you don't really get a sense of it, then do the ones that I've missed out as well to give you more practice. And what I'll do is I will just come around and help people one-on-one.